Hey folks, Professor Fiore here. Today we're going to talk about loudness. Loudness is the human perception of sound pressure level. These two things are often confused. They're not the same thing. They are correlated, but they're not identical. If you are talking about a value of dBSPL, like, hey, I was at the concert last night, it was 105 dBSPL, you're talking about sound pressure levels, you're not really talking about loudness. We use these two terms interchangeably, unfortunately, but technically they are different, and that's what we're going to talk about in this video. In fact, there is a separate unit for loudness. We don't measure loudness in dBSPL. That's a sound pressure level. Loudness is measured in fons. All right. Where does this all come from? What are we talking about? What's the history on this? Well, it was discovered some time ago, back in the 1930s, that you could have different sound pressure levels at different frequencies that people would say were equally loud. Or another way of looking at that is to say, I could have two different frequencies, let's say like 50 hertz down in the bass and 1 kilohertz, in the mid-range. I could have these two different frequencies and they could be at the same sound pressure level, let's say 70, 80, 90 dBSPL, but people would listen to them and say one is louder than the other. Now, if loudness and SPL were identical, that wouldn't be the case. You could use these things interchangeably. In other words, any frequency at one SPL would be just as loud as any other frequency at that same SPL. But it does not work that way. It turns out that your ear is very sensitive to certain frequencies and not very sensitive to other frequencies. And actually that sensitivity, the relative sensitivities, changes with the overall volume level. So it's sort of, multiply complicated here, okay? So there were a couple of researchers back in the 1930s named Fletcher and Munson, and they did a little experiment. Basically, I'm going to recap how you would do the experiment yourself. So you would get a nice calibrated sound source, like a pair of headphones. Right? You wouldn't want to do this with loudspeakers in a normal room because of resonant modes and things like that, which will mess up your results. You could do it in an anechoic chamber, but most people don't have one of those handy, so headphones it could be. So if you knew these headphones had a perfectly flat response, perfectly even response, what you would do is you would take a pair of frequency generators, sine wave generators. You would set one as your reference. And our common reference would be 1 kilohertz. Right? That's very, very common to have a reference frequency in audio of 1 kilohertz. All right, so the reference frequency is 1 kilohertz. All right. So what we would do is we would set that up to a certain SPL level, right? You listen to it in the headphones. And then we would have the person, little switch, we'd have the person listen to a different frequency, right? Maybe 50 hertz or 200 hertz or 5 kilohertz, something removed from this 1 kilohertz reference. And we say, okay, I want you to adjust the volume control on this thing such that these two sounds are equally loud. When I flick back and forth between them, little switch will go back and forth between them, adjust the volume so they sound equally loud. Okay, so you just give the guy a little volume control knob, right? And he or she cranks that thing up and down until they decide, yes, this is equally loud to my reference. Then you as the experimenter, you could go back and write down what the voltage is out of the amplifier or something like that. You'd have, technical knowledge of your playback system, obviously, hopefully, better. So you could write that down. Then you would change the frequency. And you would say, okay, let's try it for this new frequency. If we just did 50, let's do 100. Let's compare 100 hertz to 1 kilohertz. And again, you adjust the volume control level until you say these are equally loud. And we just keep doing that, right? So maybe we'll do it for 20 different frequencies, let's just say. So I now have a table. I have a table of data that indicates what the appropriate volume settings are, what the appropriate output voltages would be for my amplifier, right, that's producing this new tone compared to my 1 kilohertz reference. Now I can take all those because I have the technical data for my amplifier and my headphones and everything else, right? I can turn that into an SPL and then sort of connect the dots and see what we get. And of course, what I would have to do is repeat this process for many, many people. It wouldn't be enough to just do it for one person, right? We would want to do this for a large number of people and then do a little statistical analysis on it, excuse me, so that we could find a mean value and we could get a confidence interval for it and things like this. But when you do that, you wind up with a curve, actually a set of curves, that looks something like this. So if I just did that for one particular intensity, we wind up with something like this. So here's my frequency axis. And as would usually be the case, this would be on a logarithmic scale. Remember, human hearing, it's all about ratios in terms of frequency, right? Factors of 2 are octaves, right? So at the high frequency, it's a lot of hertz. Down here, it's not so many hertz, right? It's an octave, whether you're going from 40 hertz to 80 hertz, that's a factor of 2, or 5 kilohertz to 10 kilohertz, it's a factor of 2, right? So we could have that sort of compressed logarithmic axis. And over here, we would have the SPL, sound pressure level. So here's my 1 kilohertz. And, I would set that up for, some particular value. I'll just pull a value out of the air. I'll just say, oh, maybe that's like 60 dB or something like that. 60 dB SPL. All right. Now I plot all of those other values. In other words, the 50 hertz, the 100 hertz, the 200 hertz, the 5 kilohertz, et cetera, et cetera, et cetera. And we see what we get. And when we do that, we get a really interesting looking curve. If humans had a perfectly flat, perfectly even hearing response, what you're always trying to get out of your loudspeakers, what you're trying to get out of your microphones and, your amplifiers and all that stuff, you like ruler flat response. Human ear doesn't do that. You actually get something that kind of goes like this. What does this indicate? Right? It's got this downward slope and so forth and this dip, right? What this would indicate is that at low frequencies, right? So this is the bass down here. Maybe I'll just, arbitrarily say, hey, that's 100 hertz. Okay. What it's saying is you would need this SPL, whatever that works out to. Okay, maybe it's 75 or 80 dB SPL. You would need that sound pressure level at this frequency in order for it to sound just as loud as a 1 kilohertz sine wave at 60 dB SPL. And then if we went to a higher frequency, maybe like 2 kilohertz, we might find that the ear is a little bit more sensitive than it is at 1 kilohertz. In other words, maybe I only need, 58 or 57 dB to get it just as loud. Okay? And then if we go to an even higher frequency, maybe I'm over here at like 15 kilohertz or something like that, toward the upper end of the, human hearing range, maybe again, that's a little bit higher. Maybe it's, 64 or something like that. Okay? Now, to compound this, if we change the reference level, the curve changes as well. It's the whole curve doesn't just like go up and down. It actually sort of distorts. If we were to bring down the level, and I'm going to exaggerate this, if we were to bring down the level, so that instead of checking 1 kilohertz at 60, maybe we did it at like 40, you might get a curve that goes like this. Notice there's a steeper slope on this bass end, okay? And there's probably going to be a little bit of a change up here in the high end. Meaning at low amplitudes, when it's relatively quiet, your ear is even less sensitive at bass. But if we went the other way, we really cranked it up. If I took my reference and I brought that up to 80, 90, 100 dB SPL, we might get something that kind of goes like this. Okay, so the variation in the low bass is not as great as it is when it's really quiet. And then the shape at the really high end might change as well. Okay, so these kinds of things, this is what these two researchers, Fletcher and Munson, came up with in the 1930s. Since then, other researchers have done their thing. They've refined this. And in 2003, the ISO, the International Standards Organization, came up with a standard, ISO 226, 2003, that sort of codified this into what we now call the standard equal loudness curves. All right, so these are called equal loudness curves. A lot of people still refer to them generically as Fletcher-Munson curves, but that's really the historical thing. Squeeze that S in there. So really, you should call those equal loudness curves. All right. You might be asking an obvious question at this point, which is, well, just how loud is a 1 dB change? And this set of curves kind of gives you a little bit of a clue into this, right? It's not a constant. People think, well, you bring it up 1 dB. Just bring it up 1 dB, I've got my equalizer and it's got a little slider on it and it says, minus 10, minus, 15, plus 10, plus 15, right? Those are the dBs, right? I just move the sliders up and down. What's a dB change? Well, it depends on what the frequency is and just how loud everything is in terms of how loud that change is. What we would refer to as a just noticeable difference, right? A JND, just noticeable difference. In other words, you could reliably, a population of people could reliably say sound A is louder than sound B, or sound A is, just quieter than sound B. That number, a rule of thumb, would be 1 dB. But it really depends on what the frequency is and just how loud that thing is. What is the sound pressure level? At some frequencies and at some amplitudes, at some sound pressure levels, you can hear a half decibel difference between the two sound sources. Sometimes it might take 4 or 5 dB before you notice a difference. Like I said, in the bass end, your ear is not really all that sensitive. In the upper mid-range, like low treble, if we start talking about 3, 4, 5 kilohertz, your ear is really sensitive up there. So, little changes make a big difference. And that's an area where you get articulation, articulation of consonants, right? So that, a P sounds like a P and not like a B or a D. So that range of frequencies helps you discern those little things. If you listen to it on an instrument, if you crank up that frequency range, 3, 4, 5 kilohertz on a drum kit, for example, you get a lot more attack on the sound, right? That's where you get the attack part. Your ear is very, very sensitive to that range. So, we can say in this sort of broad kind of way, well, 1 dB is, a round figure for a just discernible difference, a just noticeable difference, but it really does depend, right? It might be half, a quarter, 3/4 of a dB. It might be, 4 or 5 dB, all depending, right? But, you can use 1 dB. If you're not talking about the extremes of frequency and you're not talking about, the extremes in sound pressure level, 1 dB is a nice, good sort of round number that you can use. The average person could discern a 1 dB change in sound pressure level. Okay? All right. So there is the question of how I relate fons to dBSPL. Well, they are identical at the reference frequency of 1 kilohertz. So if this is 60 dB SPL at 1 kilohertz, this black line here would be called the 60 Fon curve. Because everywhere along this black line, that represents an equivalent loudness level. 60 Fons is 60 Fons is 60 Fons, right? As you know, Shakespeare would say, right? A loudness level of 60 Fons by any other name is just as loud. So it might turn out that, you know, 1 kilohertz, that would require 60 dB SPL. At 100 hertz, it might require, you know, 75 dB SPL. At 3 kilohertz, maybe it only requires 57 dB SPL. But 60 Fons is 60 Fons. It's always the same. That's loudness. You say this is 60 Fons and this is 60 Fons. They're equally loud. Okay? So that's what that black line would represent, a 60 Fon curve. So if you're talking 1 kilohertz, dB SPL and Fons are the same. If you're talking any other frequency, they might be the same, you know, like that's the same level, right? So whatever that frequency happens to be, or if I continue out here, whatever that frequency happens to be, you know, they just happen to be 60 dB SPL and 60 Fons. But, you know, for the vast majority of this, right, except for those, you know, just occasional coincidental things, 60 Fons is not 60 dB SPL. 70 Fons is not 70 dB SPL. You know, 50 Fons is not 50 dB SPL. It all depends. All right. I'm going to make another video that's going to show you exactly how to do this. Instead of my rather crude drawing, I'll have some appropriate, you know, I'll have the ISO standard curves, and we can actually figure out exactly, you know, frequency A versus frequency B. What is, in fact, equivalent. All right. That's useful to know. And some of this is kind of surprising. Some of this is sort of, you know, eye-opening. Maybe it's ear-opening. The kinds of things that happen here. All right. And before I go any further, there is one thing to understand about loudness. Your ear is sort of super logarithmic. In a preceding video, you know, we were talking about decibels and the fact that, you know, a factor of 2 in power, if I were to go from like 1 watt to 2 watts or 50 watts to 100 watts, something like that, a factor of 2 is 3 decibels. Well, is a factor of 2 in power the same as a factor of 2 in loudness? It turns out it's not. Your ears sort of super compress this. That's why I call it like super logarithmic. For a subjective doubling of volume, it doesn't take 3 dB. This curve sort of suggests that it's a sort of a dynamic thing. It depends on just how loud it is and what the frequency content is. But as a general rule of thumb, to double loudness, so that, you know, I play a sound, maybe a song, and I say, okay, think about how loud that is. I'm going to turn the volume up on my stereo, and you tell me when it's twice as loud as it used to be, right? We check a bunch of people. We get a nice statistical analysis on this. That's going to take around 8 to 10 dB, right? To double the loudness, the subjective doubling of loudness, not a doubling of sound pressure, not a doubling of power, but a subjective doubling of loudness, right? The human perception of sound pressure level, right? It's going to take around 8 to 10 dB. Now, you might remember power, 10 dB is a factor of 10. That's the difference between 1 watt and 10 watts. It's the difference between 100 watts and 1,000 watts. So if you're playing your stereo, right? Let's say you got a 100-watt stereo, and you think, well, this is loud. I like it. It's low distortion. It's got everything I want, but I wish it was louder. Okay, I would like it to be twice as loud. Now, the average person would think, well, I got a 100-watt stereo. I need a 200-watt stereo. Now, according to this, you actually need about a 1,000-watt stereo to make it subjectively twice as loud, right? Assuming, of course, the loudspeakers could withstand, you know, the increase from 100 watts to 1,000 watts without distorting or turning into dust. So that's something to bear in mind. You know, if your goal, for example, if you want to upgrade your car stereo or your home stereo, and you've got, you know, again, just to use a round number, you got a 100-watt amplifier, and you're, yeah, it's great. I love it. I just want it to be a little louder. It's senseless to go out and sell that 100-watt amplifier and get like a 150-watt amplifier or even a 200-watt amplifier. You're not gaining that much. You're not going to make it twice as loud. I mean, hopefully there are some other features and factors that figure into this thing. I'm not saying you should never upgrade from a 100-watt amplifier to a 200-watt amplifier, because like I said, there's other things there. But if everything else is equal and your goal is just to make it twice as loud, going from 100 watts to 200 watts ain't going to cut it. It's not going to work. It'll be a little louder, but it won't be a lot louder. It won't be twice as loud. Okay? All right, so the last thing I want to talk about here is, because we have this weird thing going on, 60 dB SPL at some frequencies is going to be way quieter than 60 dB SPL at other frequencies. How do I compensate for that? Well, we compensate for that when I measure something. If I have an SPL meter, right? If I want to turn my SPL meter into a loudness meter, I need something to compensate for that. And this is where we come up with the idea of weighting curves, right? A weighted curve. And the most popular one, there are several of them, but the most popular one that we use is something called an A weighting curve. So this axis would represent a decibel gain in the amplifier, right? This is an electronic amplifier. And this is dB. So here's my 0 dB level, right? In other words, what comes in is what comes out, 0 dB. If I had a perfectly flat amplifier, it would be, like this. And then at some really high frequency, beyond human hearing, this thing would roll off because there's no sense in amplifying things we can't hear. Same thing at the bottom end, right? But to kind of get an idea of what we would call broadband kind of sounds, like conversations, people talking, that's not a single sine wave, it's multiple stuff. And I'm trying to sort of compare things. We come up with this A-weighted curve, right? An A-weighted curve. And if we do that, we actually talk about, on a meter, that's dBA as a unit, because it's an A-weighted curve. And an A-weighted curve looks something like this. Let me change the color here. It's notably absent at the base and at the extreme highs. Why? Because your ear is not very sensitive for bass frequencies. So, if you were measuring something, right, like I've literally done this. I've gone out to a big open field where there are turbines, wind turbines, right? And people say, oh, those things are so loud. They're not. But if you have an SPL meter and you have it on a flat response like the black curve, you might get a lot of really low frequency energy way down here, right? You might get a lot of infrasonics, as a matter of fact, things below the range of human hearing. Too low a pitch for people to hear. And the energy levels could be, relatively high, and your SPL meter could show a pretty big number. But subjectively, it's quiet because your ear is not very sensitive at those frequencies. So we would instead use this A-weighted curve. We would measure things in dBA. And this is what we would use, if we were doing noise measurements like in a factory floor, right? To figure out whether or not you need hearing protection or just how much hearing protection. We would do something like this. Your ear's not really sensitive down here, so let's compensate with this curve. And if you think about it, this curve is sort of the equal loudness contours turned upside down, right? The general shape of the equal loudness curve looked kind of like this, right? I know it has some squiggles in it, but it's basically this curve turned upside down, okay? So that's the idea, is to compensate for that so that I can make an even comparison, right? Sort of an apples to apples kind of comparison on these different noise sources, right? So I would use a dBA scale rather than a flat scale. Think about it this way. If you had an amplifier and it had a high frequency limit that, went out to let's say a megahertz, and there was a lot of noise out there up at the, 100 kilohertz, 200 kilohertz, 500 kilohertz. You measure that on an oscilloscope or something, you have all of this signal, all of this noise, and the numeric value is not going to look very good. But it's going to sound a lot better than that because you can't hear anything over 20 kilohertz. So it actually makes sense to have a curve that like drops off at the top end of human hearing. So if you're going to test something like an amplifier, you would use a C-weighted curve, which kind of looks more like the black thing rather than the red one, just to get rid of those extremes outside the range of human hearing. All right. But if we're just talking about environmental noise and so forth, dBA is a very common one. There are other standards. dBA isn't perfect, but it's a standard that has been in place for a long time. You're going to see it. It's out there. It's useful, right? So in quick summary, loudness is the human perception of sound pressure level. It has units of phons. It uses a reference of 1 kilohertz. So X number of dB SPL at 1 kilohertz is that same number, X phons. If we look at any other frequency, that value could be considerably different. The shape that we get, this sort of blue-shaped curve, that's what we call an equal loudness contour. And those alter not just with frequency, but they also change, they warp as the overall sound pressure level goes up and down. And then finally, to help compensate when we do measurements, we have weighting curves that sort of imply the inverse characteristic so that we have a better idea of our human subjective interpretation of what that sound pressure level is. Okay? All right, so next video, we're going to look at some examples, numeric examples, nice graphical examples of the equal loudness contours, and I'll see you then.